one of the Pacific Northwest's most active underwater volcanoes, is showing signs it could soon erupt, and its last eruption was in 2015.
Beneath the seemingly endless expanse of the Pacific Ocean, a moment of staggering and terrifying significance has recently unfolded, sending shockwaves not just through the Earth's crust, but through the global scientific community. It all began with a sudden and highly unusual seismic event detected deep in the ocean basin, thousands of meters below the surface, where human access is limited and light has never reached. This wasn't a typical earthquake, nor was it a volcanic tremor scientists have seen before. What occurred in that remote abyss stunned experts monitoring tectonic activity, and its implications have set off a storm of analysis, concern, and speculation. Before we start, smash the like and subscribe buttons for more updates. The seismic signature that drew immediate attention came not with the classic profile of an earthquake, but as a complex, deep rumbling harmonic tremor that lasted far longer than usual seismic events. Its amplitude was erratic but powerful, and the frequency patterns pointed toward a kind of geological activity previously theorized, but never observed with this clarity. Seismographs from multiple Pacific Rim stations recorded the anomaly nearly simultaneously, its reverberations powerful enough to pulse across tectonic boundaries, yet mysteriously lacking the surface destruction normally associated with such a potent event. Beneath the ocean floor, something had shifted, something colossal and previously hidden. Initial data pointed toward the Tonga Trench, one of the deepest parts of the Earth's oceanic crust, a site where the Pacific Plate plunges beneath the Indo-Australian Plate. But when remotely operated submersibles and sonar mapping tools were dispatched to investigate, the results revealed far more than a simple tectonic adjustment. In the space of a few hours, a segment of the seafloor measuring several kilometers across had undergone a dramatic vertical displacement, dropping hundreds of meters almost instantaneously. This wasn't just a landslide or a collapse. It resembled what some have described as the Earth's crust unzipping along a fault line that had shown no prior indication of such volatility. What made this event even more baffling was the manner in which it occurred. Traditional subduction events, while immensely powerful, follow a certain known rhythm. The plates grind together, pressure builds, then a sudden slip releases energy in the form of an earthquake. But this event lacked that rhythm. Instead, sensors recorded a kind of rolling descent, a cascading failure of crustal integrity that resembled the controlled implosion of a building. There were no precursory tremors, no gradual buildup, only the sudden and terrifying confirmation that a massive swath of Earth's outer shell had yielded to an unknown force. As scientists scrambled to model the mechanics of this collapse, another revelation came from satellite altimetry data. The sea surface itself had shifted, subtly but noticeably, in response to the changes deep below. It wasn't a tsunami, no massive wave had formed, but rather a sustained low-frequency oscillation in sea level that spread across hundreds of kilometers. This phenomenon is often associated with undersea volcanic eruptions or meteor impacts, yet no such eruption or impact had occurred. The ocean had heaved in response to something else entirely. Delving into the geological archives, researchers began comparing this anomaly with ancient records from core samples taken across the Pacific. What emerged was an unsettling pattern. A series of similar, though less dramatic, crustal anomalies appear to have occurred roughly every 10,000 to 15,000 years. Each one correlated with significant disruptions in oceanic currents and marine life extinction events. It became clear that what had just transpired might be part of a cyclic planetary process that humanity has never before witnessed firsthand. The implications of this possibility are chilling. If the Earth's crust is capable of undergoing such spontaneous structural failures at this scale, then entire systems we rely on, tectonic models, earthquake forecasts, even predictions of volcanic activity, may be built on incomplete assumptions. The event beneath the Pacific may not have just been a geological curiosity. It could be a glimpse into an Earth process that is more volatile, more unpredictable, and more powerful than previously imagined. Further investigations revealed that the epicenter of the event aligned suspiciously close to a known ultra-low velocity zone, ULVZ, a mysterious feature deep in the Earth's mantle where seismic waves slow dramatically. These zones are still poorly understood, but some scientists believe they may represent regions of partially molten rock or even vast accumulations of subducted crust. If the recent event interacted with one of these ULVZs, it might have triggered or been triggered by deep mantle dynamics that surface science has only begun to grasp. The planet, it seems, may have spoken from its hidden heart, and the message is still being deciphered. Adding to the mystery was the detection of an unexplained electromagnetic burst that coincided exactly with the initial tremor. Instruments on ocean floor sensor arrays captured a pulse of energy, brief, intense, and entirely out of place. This burst, occurring within milliseconds of the crustal shift, has led to wild theories, some of which stretch into the speculative fringe. But even the most conservative scientists admit that its presence cannot yet be explained by known physical processes. Whether it was the result of mineral piezoelectric discharge under extreme stress, or something even more exotic remains unknown. But the mere fact of its existence has upended previously stable models of how Earth's crust behaves under pressure. As analysis continues, marine geologists have uncovered massive fissures newly formed across the seafloor. These aren't the typical thin fault lines, but yawning cracks wide enough to swallow submersible drones and deep enough to vanish from sonar detection. Their presence suggests that the event may have opened a new phase of tectonic activity in the region, potentially awakening ancient fault systems that had lain dormant for eons. The Pacific Plate itself, long considered a relatively stable behemoth in plate tectonics, may be undergoing a reconfiguration, one that could have global consequences in the coming decades. Beyond the geological and geophysical domains, oceanographers have raised concerns about how this event could disrupt deep ocean currents. These currents are driven by subtle differences in temperature, salinity, and seafloor topography. A vertical drop and displacement of this magnitude could potentially reroute or destabilize sections of the thermohaline circulation, sometimes called the ocean's conveyor belt. If that system shifts, even slightly, it could send ripple effects through global climate patterns, altering weather systems, precipitation cycles, and possibly even the viability of some marine ecosystems. In the biological realm, early reports from remotely operated vehicles have revealed something equally disturbing. The collapse zone appears to have obliterated several known deep-sea habitats, home to species found nowhere else on Earth. Entire microbial ecosystems, adapted over millions of years to the high-pressure, low-light conditions of the deep ocean, may have been annihilated in minutes. Scientists worry that this kind of catastrophic habitat loss could be far more common than previously believed, and that the deep ocean, long thought to be a place of slow, steady change, might in fact experience violent upheaval far more often. Adding to the unease is the fact that this event occurred without any human warning. Despite the growing network of deep ocean monitoring stations and satellites, no system detected the impending shift. There were no indicators, no signs from pressure data or seismic foreshocks. It happened in geological silence until it didn't. This has prompted a fresh wave of urgency in the scientific community to expand and enhance deep-sea monitoring infrastructure. The inaccessibility of the ocean floor, combined with the extreme pressures and darkness, makes it the most understudied part of the Earth. Now it may also be the most dangerous. Several researchers are now modeling potential chain reaction scenarios, how one event like this could trigger others. If stresses have built up in similarly unstable zones across the Pacific Plate, a cascading sequence could be possible. That would mean not one isolated anomaly, but a series of crustal failures, each feeding into the next. Such a process might unleash a series of deep ocean quakes, seafloor collapses, and even undersea volcanic eruptions, all with the capacity to reshape the physical contours of the ocean and the conditions of life on Earth. There is also a growing awareness of the potential link between these deep Earth processes and phenomena at the surface. Some climatologists are now investigating whether sudden tectonic changes at depth could influence atmospheric pressure systems, particularly those over ocean basins. While the mechanisms remain hypothetical, the concept is simple. If the seafloor shifts enough to disturb ocean currents and temperatures, then the air above will respond. Storm patterns, jet streams, and even the development of hurricanes might ultimately trace their roots to the restless shifting far beneath the waves. As the scope of this event becomes clearer, international scientific agencies have begun coordinating new expeditions and studies to understand its scope. From the United States NOAA to Japan's JAMSTEC and Europe's EMSO networks, there is a collective recognition that the deep Pacific may hold more secrets and more threats than previously considered. The cooperation is welcome, but the underlying concern remains. If this happened once, without warning, what's to stop it from happening again? What terrifies scientists most isn't just the magnitude of what occurred, it's the sheer unknown of it all. Earth's deep interior, especially beneath the oceanic crust, is less understood than the surface of the Moon or Mars. This event has illuminated just how much lies outside the boundaries of current knowledge, how vulnerable human understanding remains in the face of planetary scale forces. While no cities were destroyed, no coastlines flooded, and no warning alarms sounded, what just happened beneath the Pacific may end up being one of the most significant geophysical events in human history, not because of what it did in the moment, but because of what it reveals about what the Earth is still capable of doing. In the abyssal dark, where no light has ever shone, the Earth groaned, shifted, and opened itself for a moment. Scientists listened, and what they heard has shaken them to their core. In the weeks following the event, the silence of the deep Pacific became more ominous than ever before. While the initial tremors and structural collapses had ceased, the quiet wasn't reassuring. It was laden with suspense, as though the Earth itself had taken a deep breath and was holding it. Instruments placed in surrounding fault zones began picking up strange signals, low-frequency pulses, not seismic in nature but distinct nonetheless. These were not aftershocks. There was no ground movement tied to them. Instead, it was as if the very lithosphere was vibrating in response to the subterranean shift, like a massive tuning fork struck from within. Geophysicists studying these pulses proposed a radical theory. They suggested that what occurred might have altered the density distribution beneath the crust, creating resonance patterns never before observed. In simpler terms, the mass redistribution in the upper mantle might have triggered a kind of earth hum, a persistent inaudible frequency humming through the rock and water. This phenomenon isn't entirely new in theory. Planetary resonance has been detected on gas giants and even in glacial movements on Earth, but never had it been so pronounced or so widespread beneath an ocean basin. The implications are immense. This hum could interfere with submarine communications, migratory navigation of marine animals, and even global positioning systems if the oscillations become more pronounced or propagate towards shallower depths. Equally troubling is the behavior of nearby hydrothermal vents, long considered stable ecosystems driven by volcanic heat. In the aftermath of the crustal collapse, some of these vents have either gone dormant or erupted with unusual intensity. Scientists conducting dive missions with autonomous underwater vehicles (AUVs) have reported superheated plumes reaching unprecedented temperatures, some exceeding 800 degrees Fahrenheit, far hotter than typical vent activity. The chemical composition of the vent fluids has changed as well. Instead of the usual mixture of sulfides and trace minerals, new compounds have emerged, some of them previously unseen in any known earthly setting. This shift in chemical output indicates that magma chambers feeding these systems may have been breached or altered. It suggests that the event didn't just collapse part of the seafloor, it tore open or rerouted some of the plumbing systems connecting deep Earth heat to oceanic ecosystems. Such disruption could trigger secondary effects, such as submarine volcanic eruptions or even the formation of entirely new vent fields. Moreover, the release of unusual elements, some potentially toxic, could poison swaths of the deep-sea biosphere that evolved under chemically stable conditions. For life forms adapted over eons to a specific thermal and chemical range, these shifts are nothing short of apocalyptic. In tandem with these geochemical changes, marine biologists have begun to observe strange behavioral shifts in deep-sea fauna. Several remotely monitored species, including the giant isopod and certain benthic cephalopods, are exhibiting disoriented swimming patterns and mass relocations, unusual behaviors for animals that normally remain localized for their entire lives. Schools of bioluminescent fish have been filmed congregating in dense, erratic swarms far from their known habitats. Some have even been observed fleeing from the collapsed zone as if driven by a primal warning, one that perhaps only these ancient organisms can perceive. What unsettles researchers the most is that these behavioral changes appear to be spreading. Days after the event, erratic movements were noted hundreds of kilometers from the epicenter. Now, weeks later, similar migrations and panics are being documented along the Mariana Trench, the Philippine Sea, and toward the Galapagos Rift. The range and speed of this behavioral contagion suggests that some deep ocean communication or sensory mechanism is responding to a signal, one we do not yet understand. Could it be vibrations, magnetic shifts, chemical cues? Whatever it is, it's moving faster than ocean currents alone could explain. Further complicating the picture is the impact on Earth's magnetic field. Several satellites in low Earth orbit, particularly those part of geomagnetic survey missions, have detected minor but measurable anomalies in the Pacific region's magnetic flux. These aren't dramatic flips or spikes, but subtle distortions, localized warping in the geomagnetic field above the area of the event. Such changes typically occur near volcanic islands or due to solar interference, not under deep ocean basins. The anomalies suggest that either molten iron deeper in the mantle was displaced, or that materials newly exposed by the collapse have magnetic properties capable of influencing the field above. One leading hypothesis is that rare metals or magnetically reactive compounds, long buried under thick crust, have been brought closer to the surface, or worse, have begun to dissolve into the ocean. If accurate, this would not only explain the magnetic anomalies but also raise alarms about long-term impacts on marine navigation systems, which often rely on Earth's magnetic cues. More alarmingly, migratory animals like whales, turtles, and even birds that navigate using magnetic fields may find their routes confused, their instincts scrambled. Already, a spike in whale beachings has been noted along Pacific coasts, although it remains uncertain whether the events are connected. Amid these emerging concerns, structural engineers and oceanographers are beginning to worry about the stability of the Pacific seafloor in a broader sense. A detailed examination of satellite topography data has revealed minute changes not just in the collapsed region, but across a network of undersea mountain ranges and ridges that stretch for thousands of kilometers. These changes, though imperceptible to the human eye, signal a slow but widespread flexing of the sea floor. It's as if the entire Pacific plate is groaning under a new kind of strain, less a singular event and more a rebalancing of geological forces. This kind of distributed stress suggests we may be entering a new phase of tectonic motion. Instead of the relatively slow drift of continents and plates, there's the potential now for more dynamic shifts, particularly in subduction zones bordering the Pacific. The Ring of Fire, known for its frequent earthquakes and volcanic activity, may be preparing to enter a heightened state of instability. If so, then what occurred beneath the ocean may be not just a one-off event, but the herald of a broader transformation in Earth's surface dynamics. One of the most dramatic revelations has come from acoustic mapping of the ocean floor following the collapse. Using advanced sonar imaging, researchers have identified what appears to be a newly formed trench-like structure near the original collapse zone. This chasm is deep, jagged, and alarmingly linear. Its geometry doesn't match that of known fault lines or subduction zones. Some have speculated it might be the beginning of a new rift, a tear in the Earth's crust not seen since the opening of the Atlantic Ocean millions of years ago. If true, then humanity may be witnessing the birth of a new tectonic boundary. That process, if it continues, could eventually split the Pacific plate and reorganize the map of the world's oceans. Adding fuel to the mystery is the discovery of thermal anomalies in the water column above the collapse. Satellites equipped with infrared sensors have detected faint, patchy temperature increases in surface waters hundreds of meters above the deep fissure. These anomalies don't follow the expected patterns of ocean currents or weather-induced warming. Instead, they form geometric plumes aligned with known fault directions, rising like unseen geysers from the abyss. One interpretation is that heated gases, perhaps methane, carbon dioxide, or hydrogen sulfide, are being released from newly exposed pockets beneath the crust and warming the water from below. Such gas emissions are a growing concern, especially methane, a greenhouse gas far more potent than carbon dioxide. If vast undersea reservoirs of methane hydrate were destabilized by the event, the consequences for climate stability could be profound. Sudden releases of methane into the ocean and atmosphere could accelerate warming trends, disrupt marine oxygen levels, and lead to unpredictable feedback loops in both oceanic and atmospheric systems. While there is no definitive evidence yet of a mass release, signs point to increased venting, bubbles rising in columns, chemical anomalies in water samples, and shifts in plankton population densities that suggest altered pH and gas concentrations. The implications ripple outward. If tectonic instability beneath the Pacific continues, or worsens, it could pose significant challenges to undersea infrastructure. Communication cables, which carry the vast majority of intercontinental internet traffic, lie vulnerable on the seafloor. Earthquakes and seafloor shifts can sever them, causing delays, outages, and massive financial repercussions. Energy pipelines, deep-sea mining operations, and future plans for seafloor colonization all rest on assumptions of crustal stability. This recent event forces a re-evaluation of those assumptions. Long-term planning for everything from global data networks to marine conservation zones must now factor in a new, unpredictable risk profile. Even without further collapses, the psychological impact of the event is profound. For centuries, humans have regarded the deep ocean as a place of slow, frozen time, a cold, dark realm immune to sudden change. This event shatters that illusion. It reminds us that beneath the calm surface of the sea lies a world as volatile, as alive, and as dangerous as any volcano or earthquake zone. It reveals that the forces shaping our planet do not operate solely on million-year timelines. They can manifest in minutes with no warning. The knowledge of this power, lurking in the abyss, has changed the tone of scientific discussion. Where once the focus was on exploration and discovery, it has now shifted toward preparedness and humility. The deep Pacific has revealed its capacity for violence, not in the form of a dramatic tsunami or towering eruption, but through silent collapse and unseen reordering. And in doing so, it has reminded humanity that we are guests on a planet whose processes are deeper, older, and more mysterious than we can yet comprehend. As teams of researchers descend into the depths once more, armed with new sensors, robotic explorers, and revised models, they do so not with certainty but with awe. The seafloor has spoken. Not in words, but in fractures, vibrations, and a raw demonstration of geologic force. What lies beneath remains a riddle, but it is no longer silent. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on what's really beneath the Pacific? What will happen? We want to hear from you. Thank you for watching and see you next time.